So today, I'm very happy with Professor Yoichi Miyazaki here. He's a specialist of function spaces and elliptic differential equations. I strongly believe that his technique is quite interesting to us. So I invited him this seminar. So I'm very interested in his talk. I'm very sorry that I have to stay away from my laboratory because of bad internet connection. Also sorry for this wearing a mask, something like this. It's very unusual for me to begin the seminar like this. Okay, so let us start. The title of his talk is A Tour of Sobolev Spaces by Muramatu's Integral Formula. So please start, Professor Miyazaki. And I'm very sorry that I have to appear very late. Please start.
Yes, thank you for your introduction. I'm very pleased to have this opportunity to speak here. I'd like to thank Professor Sawano, Professor Goldis, and the organizing committee. And today, I talk about the usefulness of Muramatu's integral formula in the theory of Sobolev spaces. Let us consider the LP-based Sobolev space of integer order n, defined on the whole space Rn. My presentation consists of 5 parts. After introducing notation, I will derive Muramatu's integral formula. And picking up some theorems in the theory of Sobolev spaces will give their proofs by using Muramatu's integral formula. Throughout this talk, we assume that the order n is a positive integer, but at the end of this talk, we allow m to be fractional and consider the possibility that Muramatu's integral formula works for fractional Sobolev spaces. We use the standard notation, LP norm, norm B, and convolution for distributions and LP function. And P prime stands for the conjugate exponent of P. And this symbol means that this inequality holds with some constant C. Partial dk denotes one of partial alpha, partial d alpha of order k. And partial d sub j denotes the partial differentiation with respect to the variable xj. And lambda mf denotes the vector consisting of the derivatives of f of order n. And we use this symbol, we mean that each component belongs to x, and we use this norm. And for a function k of x and positive t, we said k sub t of x equals t to the power minus m times k of x over t. Let us derive Muramatu's integral formula. The idea due to Muramatu's is very simple, and it is related to the regularization by modifiers. Let phi be a infinity function supported on the unit ball and let the integral of phi equals 1. And then the fundamental calculus gives this equality. And partial derivative of phi t is given by this if we set m of x is given by this formula. So we have this equality. In this equality, we let epsilon tends to 0. Then we have this formula. In Muramatsu's integral formula, it is very important that the function m is written as a derivative of some function. We have now it's a differentiation is over order 1. So it is more convenient that if m can be written as a sum of derivatives of higher order. And to do so, we take a function rho satisfied in these conditions and set phi like this formula. Then this m is written as like this. This is a derivative of order n. So n can be taken arbitrarily. So we have this formula. We call this formula M0. And in this formula, we want to move the differentiation from M to F. So observe that if we take out this differentiation outside and move to F, then we have this factor, t to the power alpha. If n is large enough, we can move only pure derivatives, and we can move only pure derivatives to F, and we have this formula. For the second term, Herder's inequality gives this inequality. And if P is finite, and we let R tends to infinity, then this term tends to 0. And hence this term tends to 0. And we have this formula for if P is finite. We call this formula M2 because it consists of 2 terms. And we call this formula M1 because it consists of 1 term. Here we compare our approach with Muramatu's original approach. And Muramatu's approach aims full generality. And he obtained this formula by substituting this right-hand side into this F. He get a slightly complicated formula. And he mainly used this formula to investigate Sobolev base of spaces of fractional order. defined on the general domain omega. And he characterizes the Sobolev function F by using the space LP L2. Our approach puts emphasis on simplicity. So we use only these simple formulas M1 and M2, assuming that the order of Sobolev space is a positive integer and that the domain is a whole space Rn.
Excuse me.
Hi.
Yes. So in this slide, you wrote that F in Sobolev space WMP over omega is characterized by T2 minus M times MT convolution F of X. So please let me know how to define MT F convolution F of X for F in LP over omega.
Please repeat.
Yes, this one.
This one, how to?
Yes, actually, so MT is a sort of convolution, but so how to say? So how do we define the convolution, or how to say? It is the F is a function defined over omega, and M of T is a compactly supported function. Am I correct?
Yes.
So in my opinion, in that case, so MTF of X is available only for X, which is inside omega, how to say, the boundary
Yes.
distance.
Yes. This characterization is special Lipschitz domain omega.
Special Lipschitz domain. I see, understand. I came to the point.
Yes.
But you said anyway, so you can characterize Sobolev function by means of Muramat's integral of the process, Muramat's formula. Okay, understand. Thank you.
Yes. When considering embeddings for WMP, the quantity m minus n over p plays an important role. We call it this quantity the differential dimension of WMP. This quantity appears in the following situation. If we define f lambda of x by f of lambda x, then the Sobolev norm of f lambda is written like this, and the principal term, in the principal term, this quantity appears. Here is a table of table of the differential dimension. LQ is a special case of the Sobolev space, and it has differential dimension minus n over q. And the Helder-Zimmermann space C sigma has differential dimension sigma. Roughly speaking, an embedding from x into y holds when the differential dimension of x is larger than or equal to that of y. Here is a list of the theorems in the theory of Sobolev spaces, and that Muramat's integral formula can deal with. And today we pick up some of them and prove them by using Muramat's integral formula. Let us start the Sobolev. Let us start with the Sobolev inequality for simple cases. Let m minus n over p is larger than minus n over q. Then we have these embeddings. The proof is due to Muramatu, and we use the formula M2. And in order to evaluate this convolution, we use Young's inequality. Let U be defined by this relation. Then Young's inequality gives this, and calculation of the norm of K is this. Then we have this inequality, and finally we get this. This means this embedding holds. And if we choose R so that these two terms I call them, that is, we choose R so that R to M equals this form, then we get this inequality. The proof is very simple. Next, we consider the embeddings into Helder-Zeeblung spaces. When this quantity is larger than 0, then WMP is embedded into the Helder-Zeeblung space of order sigma, and this inequality holds. Here, the seminorm F bracket sigma is defined by using the difference operator delta H, and like this. The proof is also due to Muramatu, and we omit the details and only say the key point. Key point is the estimate of this kernel. This kernel can be evaluated in two ways, and the integral is finite. So we go to next. Next, we consider the Sobolev inequality for this case, and we have this include embeddings. In this case, we go back to the previous proof. Then, in this case, this part equals 0. So the integral is infinite. So this method cannot work. So we need a different method. Muramatu's original method is to use this estimate. It is obtained from Muramatu's integral formula. This is like the Sobolev representation formula, and use the Hardy-Littlewood Sobolev inequality for the least potential. This is the form of this potential. Here we give a proof of incorporating the method of Hedberg, who derived the HLS inequality by using Hardy-Littlewood maximal function. Recall that the maximal function MF is given by this formula. For the proof, we use M1 and we evaluate this convolution in two ways. Since K is supported on the unit ball, and hence the function KT is supported the ball of this ball. So this integral can be estimated by the maximal function mg. On the other hand, Herder's inequality gives this convolution is bounded by this. Then we use this bound for the interval 0R, and we use this bound for the interval R infinity. Then we get this estimate. Then choosing R suitably, then we get this inequality. Then the theorem follows from the LP boundedness of the maximal operator if P is larger than 1. For the case P equals 1, we can deal with it by using the fact that maximal operator is bounded from L1 to weak L1 space. But we omit the details. We next consider the defined Sobolev inequality for this case. If F belongs to the space of tempered distributions and satisfies nabla MF belongs to LP and F belongs to the homogeneous space of negative order, order minus N over Q. Then F belongs to LQ. Then we have this inequality. Here, the homogeneous space of order of negative order is defined by using heat kernel. Its definition is like this. And here, GT of X is the heat kernel, but we change this place by T squared, not T. So in order to avoid half integers, right? This is our definition of the homogeneous space of negative order. And it is easy to see that the refined Sobolev inequality implies a standard Sobolev inequality. Since F is in LQ, we can use Herder inequality and calculating the LQ prime norm of GT, then we get this. And this means the base of norm is bounded by FQ. So, so inserting this place FQ, then we get the usual Sobolev inequality. The refined Sobolev inequality was proved by Ledoux for m equals 1. And Dow-Lam rule proved in general case using the heat equation. We can give a proof, another proof, by using Muramatu integral formula. To do so, we use the fact that any Schwartz function can be written in terms of heat kernels. And here, the function eta k satisfies this inequality. This is L1 norm of eta k, and bound is this. And for any n, the fact is found in Stein's book. So in the second term of M2, we evaluate this like this using this formula, and this infinity is bounded by L1 norm and L infinite norm. And L1 norm satisfies this. And heat kernel norm satisfies this by the definition of the homogeneous base of space norm. And this sum is finite. We get this bound for the second time. And for the first time, we can usually estimate it. And from this inequality, we can get defined Sobolev inequality easily. Next, we consider the Schrödinger's inequality. Schrödinger's inequality was proved first by Strickers, but Ozawa improved his estimate like this. When n minus n over p equals 0, just set phi p of phi p like this, then this inequality holds. For the proof, we follow the usual way, and we use the Sobolev inequality in the embedding WMP LQ for this condition. Now we go back to the Sobolev inequality for simple cases. In the case of Schrödinger's inequality, we have this term equals 0. So the integrand is q t to the power q over n over q. So calculation shows q like this. So q appears. So q appears. So, but this q yields this part instead of this expression by 1. If we want this exponent, we must improve this estimate. Improvement was obtained by Ozawa, and we can obtain this constant q to the power 1 over p prime. As a generalization of this lemma is found in the paper of Kozono and Wada. They replace this p by any r. We prove the lemma by using Muramatu's integral formula using M2. In Muramatu's formula, we interchange the order of integration and the convolution. In Muramatu's formula, it takes the form kt convolution t g like this. We take the convolution first. So we evaluate this term first. To do so, we set hj. We set hjk like this. Then Muramatu's formula becomes like this. And hj can be estimated by this way. Then calculation shows this inequality. From this part, we can evaluate like this. So the lemma is proved. For the proof of Schrödinger's inequality, we apply this lemma with q equals kp prime to evaluate the power series. So we get Schrödinger's inequality. We'll use this lemma later. And next, we consider the classical Gagliardo-Dielenberg inequality. Let RPQ satisfies these conditions, and F belongs to LQ, and nabla MF belongs to LP. Then nabla KF belongs to LR. Then we get this inequality. Let us compare the differential dimensions in both sides. Left side the differential dimension is given by this quantity. And on the right side, differential dimension of this part is m minus n over p, and the exponent is here. And the differential dimension of fq is given by minus n over q. And this exponent is here. So, and comparing the differential dimension, the left-hand side differential dimension is between the right-hand differential dimensions. To prove the classical Gl inequality, we apply Muramatu's formula M2 to the derivative of Kf. And in that formula, we move partial dk to kj. And this time also, we move the differentiation. Then the convolution, we evaluate convolution as before, and it is bounded by the maximal function. So from this formula, we get this inequality using maximal function. And finally, we get this bound. Then choosing R suitably, we get this pointwise inequality. This inequality was already obtained by Maja, Chapeau, Shuniqua in 1999. And they use the Sobolev representation formula. Now, from this inequality, we calculate as follows. The integral is estimated by Herder's inequality, and using the LP boundedness of the maximal operator, we get this, and thus, and the N inequality follows. And this is a classical inequality, but it will be it can be improved by using VM model when P equals infinity or Q equals infinity. There are three cases. If Q only is infinity, we have this. This part is replaced by VM model. And if only P is infinity, we have this inequality. And both of P and Q are infinity, we have this inequality. Here, BMO norm is given by this formula. And concerning on case one, Meyer and Riviere proved for the case M equals 2 and K equals 1. And Strzelecki proved case 1 for general case using the duality of Hardy space and BMO space. Case 2 and case 3 are new result. This improved inequalities can be easily proved by using Muramatu's integral formula. We only slightly modify the proof for the classical Gl inequality. Instead of this estimate, we evaluate this convolution as follows. If the integral of k is equal to 0, then we can add this term. And since k is supported on the unit ball, we can evaluate this integral by BMO norm. So the other part is the same as the classical Gl inequality. After my result was published, Dow and Lamley obtained this extended theorem. They showed that BMO norm can be replaced by the homogeneous Besok norm of order 0. They use the heat equation for the proof. Here we can give a proof by using Muramatu's formula M2. We write the second term like this and observe that F in B0 implies the derivative of belongs to the Besok space of order minus k. And we use this inequality. This comes from the definition of the homogeneous Besok norm, and this comes of this. And we can evaluate this term like this. So the second term can be evaluated by this. Well, I had little time, so I must hurry
You
up.
still have 10 minutes. You still have more
Okay.
10 more minutes.
10 minutes. Oh, I see. Thank you. We next go to British Galway inequality. This theorem is formulated like this, and we use Muramatu's formula to prove this theorem. And the first term can be estimated as usual. And for the second term, we borrow the idea of Ozawa. This by Herder's inequality, we can evaluate like this. And for any R larger than Q. And FR is estimated by the Sobolev inequality from the lemma. This lemma. This using this lemma. And we set capital R and small r suitably, we get BGW inequality. Finally, we consider Bredis-Wenger inequality. It says that F has almost Lipschitz continuous. The proof is easy. We use Muramatu formula M2 and using this part M plus 1. And the first part, first term can be estimated as usual. And for the second term, we use mean value theorem in this inequality. And for the derivative of f, we can use the lemma for the Sobolev inequality. And we get this. This idea is also borrowed from Ozawa's paper. And we get this. And finally, we choose R and Q suitably, then we get BW inequality. We proved some of the theorems in Sobolev spaces. And now finally, we consider the fractional Sobolev spaces. We allow M to be fractional. And fractional Sobolev space is given by this. And record Muramatu's formula M0 is written in this form. And M is given by this. Then for the convolution, it can be written as like this in the Fourier space. And we add this term, these three terms. Then this part, from this part, fractional Laplacian comes. And from this part, if we set K like this, then this part can be written K sub T. And K sub T is infinite function and L1 and L infinity. And thus we get this formula. But in this case, K is not the Schwarz function, but K satisfies following good properties. First, the integral of K is 0, and the size of K is bounded by this function. And third condition and the fourth condition follows from this inequality. So these properties enable us to deal with fractional Sobolev spaces. But excluding the case, we must exclude the case concerning the homogeneous base of norms, and when P equals 1. Here is a list of related differences. That's all I have to say. Thank you for your attention.
Thank you for a nice talk. Are there any questions or comments? Okay, so first, Daniel, so go ahead.
Maybe first from the audience, are there any questions I can ask still later?
Okay.
Yes.
Are there any questions or comments? Just a second. Okay, so Daniel, once again, you may go ahead.
Okay.
I'd like to ask him a question, but you can do that first.
Okay, thank you, Professor Miyazaki, for this interesting talk. So there are Sobolev inequalities recently or relatively recently proven by Rossoton and Xavier Cabret, and they have, instead of the Lebesgue measure, they have a density which is polynomial. So T x1 in the power of a1 times xd in the power of ad, and of course on Rd, on the full space, but the exponents are non-negative. So there might be some exponents which are equal to 0 and so on. So I'm wondering, since this is still on the full space, but the density is different, so it's with polynomial weights basically, do you think that this method could also be worked out to establish the Sobolev inequalities?
What are you talking about? You said something.
Yeah, so replace the Lebesgue measure in the Sobolev, in the simple Sobolev inequality by the Lebesgue measure multiplied with a polynomial weight. For instance, let's say x1 in the power of a.
Weighted case.
Yes, a weighted case.
Space. Somehow there is weighted Sobolev space, but not using Muramatu's formula. But if we can evaluate this composition by something, then we can apply Muramatu's formula for that case.
Mm-hmm. I see. Okay, so this is.
Yes.
Okay. Thank you.
Yes, thank you.
Are there any questions or comments? I'd like to ask a question. So could you please go to page 21?
21, yes.
Yes. So in this slide, so you have a BMO estimate from the line 2 from above. Yes, K convolution G is estimated by BMO function, the normal BMO normal of G, right? Yes.
Yes, yes.
So do you use Lebesgue differential theorem to prove this? Because we have to replace G of X by something else. So I simply wonder, how do you prove this inequality?
This part?
Yes.
Yeah. Yes. I mistake.
So T is not so important, I suppose.
All right. This term.
Yes.
Yes. I see. I mistyped this. I think.
But yes, so you wrote something by blue. So you wrote G of X here.
G of S.
And the modulus,
Yes.
yes. So how do you control G over X in this situation? So do you need to use something, how to say, Lebesgue differential theorem or something like this?
I'm sorry. I must write this part. G, mean of G over.
I see. That's the point.
I'm sorry.
It should be correct. So B stands for the ball centered at X and radius T or something like this. Understand?
Yes.
Okay, thank you. I think that we don't have enough time now. So once again, so I'd like to ask you, are there any questions or comments? Everybody? If there is no further questions, so let's thank speaker once again. So we end this talk.
Okay, Ben, should we close the session?
Yes, we can remind about the coffee break. Probably everyone received an invitation to coffee break that will start in a few minutes.
Okay, thank you.
Sure.
Thanks, Ben.
Sorry, unfortunately, I cannot show up, but I can attend